Hello students, today I would like to discuss in detail about a mathematical function that is widely used in quantum mechanics, in electronics engineering, in photosciences, in image processing, in signal processing, in audio video analysis, image processing like audio signal processing, in several areas. This Fourier transformation or Fourier series or Laplace transform is being used. Now basically we will be all having this particular function used at all points while we do convolutions also. So this particular function, Dirac delta function, is the solution to that transformation. So first of all, let us learn what is a Dirac delta function. I will first show you graphically what it is to get an idea of it, and then I will define it mathematically. A Dirac delta function looks like this. Suppose if I draw the function delta x, which is the Dirac delta function represented by delta of x, on y-axis, that is the value of the Dirac delta function on y-axis versus the value of x, then this function value is only defined at x is equal to 0, and that is infinity. So this function is only defined at one point, that is at x is equal to 0. At x is equal to 0, this is defined, and it goes over to infinity. So this is defined at x is equal to 0, and at all other points delta x is equal to 0 at all other points, that is x is not equal to 0. So at every other point that goes up to positive infinity or up to minus infinity, the function value is 0 except only at x is equal to 0, where it becomes infinity. Another useful property of this Dirac delta function is, if you take the area under the curve, that is when you integrate it from minus infinity to plus infinity, the area under the curve is 1. This I will mathematically prove in the next coming session. Like I will be doing it right now. So these are the important properties of this mathematical function. Let us see any function which behaves like a delta Dirac function, and we will solve it and show that the area under the curve is 1, and we'll show that it doesn't depend upon another properties also. Let us consider a function, for example f of t, which is a function of time, which is integrated in the range of minus infinity to plus infinity. This is Euler's formula that defines the summation of a real part and imaginary part, e power I theta. E power I theta is cos theta plus I sin theta. This function, when integrated between minus infinity plus infinity, behaves like a delta Dirac function. Let us see. So first of all, I will integrate it between a finite discrete points, and then I'll take that discrete point to infinity so that it can be easy to understand. It will be easy to understand. So first of all, I will integrate this to minus t to plus t, and then I will limit this function to t to infinity. This I will do as a second part. First I will do the first part. This is second part. Okay. First I will integrate this one. So once I integrate, I'll get this as very easy integration. Now we know that e power I theta is cos inverse I sin theta, e power minus I theta is cos theta minus I sin theta. Now when I take a difference in between these two, I get e power I theta minus e power minus I theta as 2I sin theta. So similarly what we get here is 2 sin 2 pi xt into I by 2 pi ix. If I cut this two, I'll get sine 2 pi xt divided by pi x. So basically this equation, this function, which was a function of independent variable t over which it was integrated, has transformed to a function which is in the form of a variable of x, and this t, which is suppose consider it as some time period which has a fixed value, so it is a constant, so it has changed this into another domain entirely. This was originally a function of time which has changed to another function which is a function of x. This x is normally frequency domain. This is the transformation of Fourier that basically transforms from time domain to frequency domain. If this I change this as x as suppose f of t, that is the frequency of t, then it will be a frequency domain. Now let us look at this function. So I integrated this function f of t and I got this result as sine 2 pi xt by pi x. If I multiply by 2t and 2t, I make this argument of the sine function same. What we know from mathematics is, suppose if we take limit x tends to 0, sin x by x, this value when x goes to 0, sin 0 is 0, x is also 0, it is 0 by 0, but it is not exactly 0, it going towards 0, like 0.0001, some value it is there, and sine of that value is also very small. So the ratio of two small values like 0.0001 by 0.0001 both are same, then the ratio is 1. It is not 0, it is going towards 0, that is the limit of it. So the value is 1. So this function, if I plot, suppose I plot this function f of t, basically this f of t has changed into some other function which is in the form of x. So f of t versus x, I would say, or you can very well write this as some other function, that is, suppose I call it as g of x. I have first carried out the integration. F of t is the function minus infinity to, let us write minus t to plus t e power 2 pi I x t dt. This was a function. Only the integration has given this part. The function is equal to integration of this, not the actual function, the integration of that function. The integration has given us this particular thing, which is a function of x. So f of t, which was a function of t, while integrated has become a function of x. So now if I plot this function, so let us say this is g of x. Now at x is equal to 0, sine 0 by this has become 1. So this ratio, when I put x is equal to 0, here or close to 0 here, this value becomes 1. 1 into 2t is 2t. Okay. So now when I take the value of x as, suppose 2 pi xt is pi, x is equal to 1 by 2t. At x is equal to 1 by 2t, the value is pi. Okay. Suppose if I keep here x value 1 by 2t, 2t cancels, 2 cancels, and pi is remaining. Sin pi is 0. Whatever this value may be, the numerator is 0. So the function value is 0 at 1 by 2t. Sin 2 pi is also 0. So 2 by 2t, 3 by 2t, and so on. And similarly on the left side, sin of minus pi is also 0. So minus 1 by 2t, minus 2 by 2t, minus 3 by 2t. So if I plot this function, it comes like this. It is 0 at these values. So this is a kind of a pulse at 0 and it is subsiding down on both the sides. So it could be called as a pulse function, a pulse waveform. It is coming. So now if I take t to infinity, this is my second argument. If I take t to infinity, if I make the t as very big number and infinity, so 2t itself becomes infinity. So this goes to infinity. When this becomes very large, 3 by a very large number, it is a very small value. So this point, or 1 by 2t, this point will become very close to 0. 3 by some very big number, suppose 2 in 10 power 20, and 3 in 10 power minus 20, that comes almost beyond, just close to 0. So the function transforms to like this. And t becomes infinity, it becomes like this. The function will become like this. The function will come up and it goes to infinity and then goes to the other side. So at 0 it goes to infinity, and this is minus x values. So this is basically a Dirac delta function which I have defined before, which is infinity at 0 and the rest at all other values it is 0. So this function, so our function sine 2 pi xt by pi x limit t tends to infinity. This function is a delta Dirac function. Or I can write the same function as this t as infinity, or the same function in t is f of t is minus, instead of t I put it into infinity, minus infinity to plus infinity e power 2 pi I xt dt. This function is actually a Dirac delta function. Okay, so this function is defined as, like we have seen that x is equal to 0, it becomes infinity, and rest at all other points it is 0. Okay, now the another property of this Dirac delta function is the area under it is 1. So there are several research papers on this for calculating the integration of it, and if you see that integration from minus infinity to plus infinity sin x by x, this has been done in various ways. One is expanding the sin x in the form of series. Then the value what we get is pi. Okay, this is purely a research topic. Presently people are finding out several ways to do this, and the result is pi. So now what we have to see is this particular function sine of 2 pi xt by pi x. 2t I have multiplied. If I take this one, so this is a pulse waveform function. Okay, this is pulse waveform function, and I will find out what is the area under this particular. Suppose if I want to find out the area under this between minus infinity to plus infinity with a step function of x, because between x, this is a function of x now, between x and this g of x, we have seen the function is like this. Okay, right now we have seen. So what is the area under this? Area under this particular curve. So that is what is from minus to plus infinity, we are finding out the area. So this particular function, now let us say that p is equal to 2 pi xt. So dp is equal to 2 pi t, and is a variable in x. This is a variable x, so dx is equal to this. Now dx is equal to dp by 2 pi t, and also pi x is equal to p by 2t. So putting this into this particular waveform, this particular equation, I'll get minus infinity to plus infinity. 2 pi xt is p. This is sin p. Pi x is equal to p by 2t. P by 2t into dx is dp by 2 pi t. dp by 2 pi t. 2t, 2t cancels out. So 1 by pi comes out and it is minus infinity to plus infinity sin p by p dp. So integral under this value will be equal to pi. That is the area under this function is pi. So this is 1 by pi into pi, this is 1. Here one remarkable thing we have to see is, here I have not made t to infinity, whereas I have calculated x. That is the area under this curve from minus infinity to plus infinity in the frequency domain or x domain, not in the t domain, whereas in this put t in this particular function. So it represents that if we put t in case of f of t, or if I keep the x in case of g of x, which is the already integrated function. So this area under this is 1, whether I keep t as infinity or w as infinity. So in case of this particular function, which is in form of x, I have not done t to infinity, t got cancelled out throughout. So the area under this, if suppose t is not made infinity, for example, if I integrate this under minus t to plus t, I got this function. I integrated only keeping x from minus infinity to plus infinity, the area is 1. So it is independent of t. The area under this curve, which is in the function of x, is independent of t, whether t is from minus t to plus t or having a discrete value, or it goes to infinity. So it represents that the function which is represented as e power 2 pi x, or the summation of exponential factors between time period, and if you integrate the area under that particular frequency domain or the domain in x, so other frequency domain, other domain, then the area is 1 independent of this being equal to infinity. So between the area or you go to infinity, the distribution of Dirac delta function is same. That is, if you take the area of Dirac function between minus t to plus t, or you take to minus infinity to plus infinity, the area is 1. So the Dirac delta function from minus infinity to plus infinity, delta of x dx is 1. T can go to infinity, or t can be any value. That is what it means. The area is 1. And for Dirac delta function, it is also 1. Or a pulse waveform, this particular waveform is also 1. Hope I could try to explain this one better.